We're going to apply Gauss's law again for a parallel plate capacitor. It's just shown here in cross section. But there's the top plate is a conductor and it's been charged. That's the negative plate of the capacitor. The bottom plate is going to have the same magnitude of charge, but it's positive charge, and that's going to reside on the upper surface of the bottom plate. For one single infinite sheet, we know that the electric field is going to point perpendicular. So I'm going to have electric field lines that exist in between the two plates of the parallel plate capacitor. Uniformly spaced. So try to draw them so that the space between the lines is the same, and the electric field lines are going to extend away from the positive charge and to the negative charge. Above the negative plate, the electric fields from the two plates cancel out, and below the positive plate, the electric fields from the two plates cancel out, and in between they add together. For my Gaussian surface, I'm just going to draw it in cross section here. But as a full three-dimensional surface, we're going to apply Gauss's law to. It's going to look like a cube, in as much as I can draw a cube. So that cube is basically embedded in here, and we're looking at it on the top down. So the area of each side of the cube is the same. So each face of the cube is a surface area A. Now, in applying Gauss's law, we're going to evaluate the flux of the electric field through all six faces of this cube. It's going to simplify quite a bit, but I want you to remember that it's a closed surface you apply Gauss's law to, and for our surface that we pick to be a cube, we're going to have to think about all six faces. Alright, so in applying Gauss's law, the flux of the electric field through my Gaussian surface is going to be all of the charge enclosed inside the surface divided by the permittivity of free space. Go ahead and label these surfaces, so we'll call this 1, so on the opposite side that's 6, and then we'd have sides 2, 3, 4, and 5. And that's just to be able to talk about it. The electric field lines are going to be beginning inside the cube and then extending through face 6. There are going to be no field lines that are going to cross our faces 2, 3, 4, or 5. And there is no electric field along face 1 because face 1 is here inside the conductor where the electric field has to be 0. This is a parallel plate capacitor that's in electrostatic equilibrium. So by inspection, the flux of the electric field is only going to come through or arise from this face. And along that face, the outward pointing normal is parallel to the electric field lines, and so the flux of the electric field is simply E times A. So we know the left-hand side of Gauss's law. We also need to calculate how much charge is enclosed. So the charge enclosed is going to be the surface charge density for the capacitor times the area of one face of our cube. Now we have both sides of Gauss's law set up, and we can fill those in. So E times the area of our cube is going to be the surface charge density of the capacitor, sigma, times the area over the permittivity of free space. And it's the same area on both sides, so that's arbitrary, cancels out. And we have the electric field for a parallel plate capacitor. The electric field is equal to the surface charge density that the capacitor is charged to divided by the permittivity. So this is the permittivity of free space. There isn't anything in the space between the two plates of the parallel plate capacitor. If we stick some dielectric material in, that will change the capacitance, and it changes the permittivity here. Instead of being permittivity of free space, it would be the permittivity of that material, taking into account its polarization. And again, with the parallel plate capacitor, it's sort of like just a superposition of two infinite sheets of charge. With a parallel plate capacitor, the electric field is uniform in between the plates, so it's just a constant, and then outside of the plates it's zero. There's no field at all. So this is the configuration of charges that gives you a uniform electric field.